It's 17 minutes after 7 o'clock on 97.1 Wadsworth Community Radio here on a Friday morning, last day in November. And in the studio with us here, we have Dr. Christopher Dellcorte from NASA Glenn. And he was he partnered up with Brian Emmons, but won the 2018 Government and Commercial Invention of the Year Award for NASA Glenn. Well, good morning and welcome.
Good morning, Tom.
This is actually sort of a return to Wadsworth, although you don't live too far away. Anybody that was down here with us, with, of course, all the wonderful people from Glenn for our May the 4th Be With You event. Chris probably took your picture.
That's right. That's right. My wife Patty and I ran the photo booth. We probably took pictures of 400 people.
Yeah, that was fun. Yeah, that was a lot of fun. Give us a little bit of your background. Of course, you live up in Sharon Center.
Sure. So I've been living in the Medina County area since the late 1980s. My wife and I moved out here from the city, after we finished up with college, and we moved to Sharon in the early 90s, built a house, and since Sharon Township is so close to Wadsworth, we've spent quite a bit of our time down here at the library and doing our shopping, and of course really enjoy all the first Friday night events. Out here to look for Santa Claus the other night.
Yeah, oh, good,
yeah. Historical Society home, and so we consider ourselves
Wadsworthians.
Wadsworthians, that's right. That's right. Certainly good neighbors.
Yes. Right. Of course, NASA's always been good neighbors as well. And number one, I know next Wednesday, December the 5th, there's a program over at the Wadsworth Public Library. I know there's someone from Glenn's coming down to do it's an Apollo 50th anniversary, I think, Apollo 7 and 8, a program on that coming up as well. So,
I think, everyone in Wadsworth should be pretty proud of, our local hero, Mike Foreman. Having an astronaut from your hometown is kind of an unusual treat.
Mm-hmm. And so where are you from originally, Chris?
So I'm originally from New York, the New York City area, and moved out to Ohio to go to college. Went to Case Western Reserve. At that time, this early 80s, energy conservation, like it is today, was a real big topic, and Case Western had a big program in energy engineering, and I went out to school for that, and it kind of stuck. And while I was there, I took a job as a grad student at NASA that was called Lewis Research Center then. They had a group dedicated to friction, wear, and lubrication, which we now call tribology. It's not the study of the Native Americans. Tribology is a word. It's not that old, maybe 40 years, 50 years old word that comes from the Greek root tribos, which means to rub. So tribology is the study of friction, wear, and lubrication. In any case, NASA Lewis had a research project at the time to make engines more efficient, and they did that through better lubricants. And so I got tagged by one of my professors to go out there as a grad student and do some research, and I've been there ever since.
And of course, all that technology, when it's one thing to, you drive an automobile down the street or whatever, but when you start thinking of, and it even happens on a car when you fire up the car, the oil's one temperature, as it heats up, the lubricity changes, all those kind of things. Well, I don't want to lose our audience here, but when you get into other applications such as space or whatever, it's a whole new ball game as far as that lubrication or that friction.
Sure, and it's really even broader than that. We were discussing regular oil lubricated bearings before we came on the radio this morning, and I didn't know you had a long history in lead tin Babbitt bearings. It's a topic that I'm always impressed with. I get a lot of questions about how often should I change the oil in my car and things of that nature. And people at NASA often ask me, they say, gee, Chris, a lot of people move around within NASA and take lots of different jobs. How can you have worked in exactly the same field and exactly the same research group for over 3 decades? And I tell them, my job at NASA is to make sure that things that are supposed to move keep moving. And moving mechanical assemblies, we find them all over NASA missions, not just in space. All your aircraft engines, think about the landing gear that has to go up and down, the bearings in the engine that have to spin, the little bearings and bushings that are in the wings, and all the flaps and elevons that have to move. It's my job to develop technologies to keep those things moving properly and lasting for a long time. And those are under extreme conditions. Airplanes fly at high altitude where it's 50, 60, 70 degrees below zero. Winds are under 500 miles an hour. And then we got our space side of NASA, and the varied space missions that NASA have expose bearings and gears and things of that nature to red hot temperatures during re-entry phases, super cold temperatures out in the darkness of space, and when we're facing the sun, temperatures can get a few hundred degrees Fahrenheit pretty quickly. So we get a chance to work in a variety of different environments, and it's a blessing and a curse. You have to know a lot about a lot of different things, but it's a lot of fun.
And it's one of those areas too where you've worked in it for 30 years, but 30 years ago, it was a whole different. I mean, it changes. I mean, it's the same, but it changes with technology. Some of the and as I notice in here, and we'll get into it here. The coatings that you did here were a plasma application. That technology to apply that wasn't around 30, 40, 50 years ago. So by some of those applications allow you to develop things a little bit differently as well with the manufacturing techniques.
And I got to say, it's a treat to be interviewed by somebody that knows something about the field. So I thank you for that. It is true that technology marches on and new technology arises, but I think it's probably more important to think about the problems that exist that drive the need for the technology. It's really a rare situation where somebody discovers something new and doesn't have any idea what they're going to use it for. What traditionally happens is that there are long-standing problems in your particular field of endeavor that you think to yourself, doggone it, I wish I had a solution to problem X. And then one day you're looking around and you see solution Y that looks like it maybe could be a solution for problem X, and so you start working on it. And in my case, that's what happened with this technology that we developed, which we call the NASA PSPM 400 technology, which got the award for Invention of the Year. The name is kind of funny, PSPM 400, and the name is a Genesis kind of a name. PS stands for plasma spray, which is a kind of a spray painting technology where you take materials you want to make a coating of and you sprinkle them into a high temperature gas plasma where the particles melt and then splat on the surface and form a nice adherent coating. PM stands for powder metallurgy. That's where you take powders of material and you smash them together at high temperature, and it forms a solid block. Not a whole lot unlike making a ceramic pot, where you have clay particles that you mix with water, you make your green state, you put it in the oven and you fire it in your kiln and it comes out solid. That's what powder metallurgy is, and we call it 400 and not 300 or 200 or 100, because I learned my trade, craft and trade, from my mentor, Hal Sliney, who taught me everything I knew for the first 10 or 15 years at NASA. And he had invented PSPM 100 and PSPM 200, and then I worked on the 300 and now the 400. And every generation of material that we invent has some sort of capability that the previous generations didn't have. And the latest generation, PSPM 400, solved a couple of long-standing problems that we had. I mean, and essentially, we're trying to come up with a material kind of like a Teflon or a graphite or a bronze kind of a material that you use for a sliding surface. We try to come up with a material that can work at much higher temperatures. So we use the material in places like the control bushings and bearings that move rocket engines back and forth so you can steer a rocket. They get nice and hot, so we need lubricants for that. We have inside aircraft engines, there are little vanes that have to turn to move the gas flow from one part of the engine to another for maximum efficiency. Those things get hot. And in a lot of those applications, prior to the development of these new technologies, we would use lower temperature materials like Teflons and graphite and things of that nature and provide cooling air and cooling water to those regions. But that adds weight and complexity. So it's been a long-standing problem that we've had this high temperature sliding wear things that we need to solve for NASA missions. And what we did with the PSPM 400 technology is we were trying to solve two basic problems. We wanted to lower costs of the prior technologies, the 100, the 200, the 300 series, and we wanted to make a material that could stand the test of time without changing. Some of the earlier materials had cobalt in them and other alloys that are really, really expensive and hard to machine, so that raised the costs. So that was problem number one. The other problem is the earlier generation materials used a lot of silver. And as you know, silver is a precious metal, and the prices have been going nothing but north for quite a while. And what we did with the PSPM 400 material is we cut back the amount of silver considerably by changing some of the other materials, and we picked materials that were what we call intrinsically more dimensionally stable. Basically, what we mean is we pick materials that don't rust and don't burn. And so over time, they don't grow and change dimension.
And when they're tougher like that, of course, you don't have to apply the thickness. I mean, again, in a babbitt application, you need a thicker babbitt to either absorb the heat or those kind of things. So in those kind of applications, you can save on the material because it's thinner.
Sure, and we're still in the early stages and of applications. So the customers that are out there in industry are just now trying to figure out how to use this stuff, and that's kind of another angle for the NASA work. It's kind of interesting that people don't realize. I tell folks that NASA has problems way before anybody else has them, because we're always trying to do new things. You try to land a probe on Venus, and you find out that Venus is 1,500 pounds per square inch of pressure, and it's mostly carbon dioxide with a little bit of sulfuric acid mixed in. And
there's a nice combination for
sulfuric acid will corrode and dissolve just about anything. Oh yeah, and the temperatures are about 1,000 degrees Fahrenheit, and so there's no environment like that here on Earth. And when we try to make a machine that can survive in that environment, all of a sudden new problems crop up. We need electronic materials like transistors that can operate at 1,000 degrees. We need lubricants and bearings that can operate in those acidic conditions at 1,000 degrees. And so there's technologists like myself and my colleagues at NASA that develop those technologies for those applications. Maybe I'm a little ahead of the game because we came up with a material that can provide lubrication on Venus, and we have it today, but our Venus probe missions are still a few years out. So what do? We file for a patent on our new technology so we can protect this technology and create American jobs instead of having the materials made overseas. That's stage number one. And then you take that technology and you advertise it through research papers and things like this award that we got is good publicity. And then maybe you have somebody in industry that says, hey, I've got a high temperature friction and wear problem inside my heat treatment furnace that I've been solving for years by continually replacing bearings that wear out or providing cooling water or something like that. And they give us a call and say, where do we get this stuff? And we send them to our licensees, our companies that have gotten an agreement from the government to make our products for us, and they build bearings out of the PSPM 400 and they sell them, and that stimulates the economy and creates jobs and solves industrial problems here on Earth.
Well, and again, as you mentioned, that some of the the things that you're going into in interplanetary space, you go out to an oil platform out in the Gulf, and all of a sudden have to replace a bearing that might be a couple thousand feet down. Well, other than the cost there just for the maintenance is unbelievable. But if you can take all that cooling and a lot of that out of there with the bearing replacement like that, all of a sudden you have just made and again, industry right here in the United States much more efficient as well.
Mm-hmm, exactly. And if people who have problems become aware of potential solutions, then they seek them out. And that oil drilling application you just mentioned is kind of an interesting one. We field calls from oil drilling people pretty regularly since that invention of the year came out, specifically because downhole temperatures, a few miles down underground are 500, 600, 700 degrees Fahrenheit, and lo and behold, what do we got down there? We got sulfide gases, which are the same kind of acids we have up on Venus. So, like I said, NASA faces these unusual problems. We solve them, and then we try to take that technology and distribute it around in other places that can benefit from it.
Chris, is it better as a researcher? Do you try to be ahead of the problem or of a potential problem, or in some cases, do you find that you're working kind of behind? There is a problem, and now all of a sudden you have to try to solve it.
Well, I that's really a good question. Given a choice, I'd certainly rather come up with a solution before the problem exists. But when you try to get funding from your managers to work on a technology that has no need, it's pretty tough to do. So I'd say it's kind of a mixed bag. I tell people that from a project standpoint, I'd rather know what problems you anticipate while we have time to work on them than wait until you're on the launch pad and something doesn't work and then it's a crisis, because developing a technology takes decades, and it's not something that you come up with a solution overnight. So what we try to do is kind of twofold. We try to always scope out what kind of recurrent problems we have in mechanical systems, and so we're always on the lookout for solutions. And at the same time, we look at what are the limitations of today's technology and how can we push it to higher and higher needs. For example, you can use things like Teflon and graphite at temperatures of 400 or 500 degrees Fahrenheit. It's not too big of a deal. But when you go to temperatures above that, there's really nothing that we can use. And so we've been working at NASA Glenn, NASA Lewis before NASA Glenn, we've been working there on pushing the temperature capability of lubricant materials beyond 500 degrees Fahrenheit for the past 50 years. And so, this PSPM 400 material is built upon a foundation of earlier research that identified the different ingredients that are in it that can survive those temperatures. It's one of those weird kind of things. If technologists do a really great job and solve all of the problems in the field, then people don't think we need that technology. So we have to strike a balance. We strike a balance of solving problems before they crop up and being there to solve problems when they do happen. And that does happen quite a bit. I probably spend half my time doing research and developing new technology, and the other half of my time I spend solving mission-related problems that crop up unexpectedly.
One of the higher orbits experiments that I believe it may have launched on the 17th of November that was going up, that the kids came up with, was a self-healing material. And that was very interesting as well, because graphene, I believe, was the I was part of the team that kind of picked that, so I knew a little bit about it, just enough to be dangerous. But those kind of technologies are really interesting. If you get a substance up there, you get a micrometeorite that might hit a surface or whatever, and have that self-healing type of and again, so what's interesting is the way that that NASA reaches out now to the public. All of a sudden, you've got a lot of neat ideas coming up from a lot of different venues, whether it's private industry, whether it's even kids and college level or whatever, coming up with some of the ideas. So I know NASA has, and of course, missions way back were a little bit different, a little bit different focus. But luckily, you're able to reach out and really be more part of industry and the community now as well.
Yeah, you're talking about engagement, and we have programs, we call it citizen science, where we're engaging the general public and encouraging people at every educational and age level to not just be inspired by what we do at NASA, but also to be engaged. For example, we may try to do a citizen science project to study algae blooms in lakes. And we ask people to go out and report on what they find in terms of algae in different places, and we then combine that with the data we get from our overflight aircraft and from satellites, and it gets everybody involved so that we get more data and we learn more, but it also raises the awareness. And that example you gave of self-healing graphene, graphene is made out of carbon, and people have been using and studying carbon for thousands and thousands of years, and carbon takes many forms. And if you had asked somebody 20 years ago, what's there left to do in studying carbon, people would probably say, nothing. We know everything about carbon. It can be coal, it can be diamond, it can be graphite. And here in the last just 20 years, we've come up with diamond-like carbon coatings that we use all over the fuel injectors of our car engines, so the fuel injectors don't wear out anymore. And we have come up with this graphene material that you can punch a hole in it, and it sort of starts moving on its own and filling up the hole almost like it was alive. So there's a lot left to be discovered. We don't even know it's out there, but I'm pretty confident that it is out there.
You got research on this took, if I believe all that is written, you started 13 or 12 years ago starting this. How do you not, and folks would get frustrated after maybe 1 year and not finding an answer, but you go a lot longer than that. How do you keep your focus on this? And when you're trying to develop something, and I'm sure there are failures along the way in that, how do you keep going for such a long period of time?
That's a really good point. And I tell people, if you want to work in research, there's a couple things you have to keep in mind. And one is that you have to be thick-skinned and you have to embrace failure. And those are kind of trite thoughts, but my strategy is to make sure I never put all my eggs in one basket. I typically am working on 2 or 3 different problem areas at exactly the same time, because inevitably one topic that you're working on is going to hit a roadblock, and if you don't have some positivity in your life and in your work, it's easy to get discouraged. So the high temperature solid lubricants that I've been working on for decades, in between when those projects were in a low point, or even concurrently, I've been working on other things. Like I worked on for many years, I worked on high-speed air lubricated bearings for oil-free gas turbine engines, and they use these high-temperature coatings for startup and shutdown periods when you got a little rubbing. So the two are kind of connected. And I work on magnetic bearings because there are certain applications where, like in an electric motor used in space, you've got electricity, you've got motor coils. Sure would be nice to not have to have ball bearings and grease up there as well. So we work on magnetic bearings for space. And most recently, the past decade or so, I've been working on a team. We've discovered a ball bearing material that can't rust and can't dent. So, that's another technology that, hey, maybe that'll be a topic for a future Invention of the Year award. We never know. So I've always got 5 or 6 things going on. And I think I mentioned earlier, I only spend about half my time on research developing new technologies. The other half of my time is spent doing troubleshooting for NASA missions and oversight for NASA missions to try to help the mission managers avoid the friction and wear problems before the spacecraft gets to the launch pad. And I think that's a strategy that's probably important in your whole life. You got to have a good family life. You need to have good health. And in the research world, you better be working on more than one thing at a time, because sure than anything, that research work is going to hit a wall, and it's easy to get discouraged.
Yeah. Anything to do with the Mars missions and that? Here I'm thinking, your temperatures there are rapidly. You talked about Venus being what you had to do there. What about Mars, which is
I can tell you that answer that in a little bit of a story. It's kind of interesting. I recall vividly. I was on vacation about 12 years ago. I was on vacation at the beach, and the cell phone coverage there was non-existent. And I was on vacation for 2 weeks, and I remember after about a week, we decided it was time to leave the beach and head into town, and got to town, turned on my cell phone, and I had 27 phone messages. And they were all from different people affiliated with the Mars Curiosity rover mission. And that was a time period where we were doing the final build of different components for the Mars rover, the Curiosity rover that's up there now roaming around taking all those great pictures. Not the one that just landed,
right?
But its predecessor. And the guys that were making all the drive motors and gearboxes in every single one of the wheels and in all the robotic arms and everything, they were doing the final tests of those gearboxes, which were supposed to run at very cold temperatures for thousands of hours, and they were failing after a couple of minutes of use. And they were desperate to get some help in the friction and wear area. And I got back from the vacation a couple of days later and got back on a plane and actually went back out pretty close to the beach where the company was building the gearboxes to help them troubleshoot. And they were having some serious problems because they didn't really understand that when the temperatures got real cold, the oils and greases that they thought were providing lubrication weren't quite cutting it, and parts were kind of going unstable and locking up and failing. And so it's interesting. You get a chance to work on something like the Mars rover, and I know I held in my hand, the gears and the motors that are up there on Mars running around now, and those guys worked really hard with a little bit of guidance from us, and they overcame those problems. And one thing leads to another, because about a year later, they were doing some of the final testing of the chemistry kit, they call it, on the Mars rover that sniffs the gases and tries to figure out what they are. And they got a big vacuum pump in that system, and lo and behold, the bearings in that vacuum pump didn't work quite right. And nobody could figure out what was wrong. And I was able to tap some of my other NASA colleagues that have expertise in specific areas to work on that problem, and we solved that problem. So it's funny to this day, if I want to get really good pictures of the Mars rover, or I want to know what's going on with it, I can pick up the phone and I can call my colleague at JPL, Kobe Boykins, who was one of these real outgoing leading project manager guys, and he always answers my calls and gives me whatever I need, because back in the dark days of that Mars Curiosity rover project, he was the guy with all the weight on his shoulders trying to solve that. So I feel pretty good. I contributed to the Mars Curiosity rover, just like thousands and thousands of other NASA employees, and we can all take pride in that.
When you talk about, Joe mentioned trying to quote unquote keep your head in the game over such a long period of time, just recently it came out, but I've already shared it with a couple people here. Michelle Lucas, again, she gave a TED talk not too long ago, and it was about failure is an option, and it is a really, really interesting, down-to-earth look at. Failure is part of the process. You can't be afraid to fail. If you're afraid to fail, you don't accomplish anything. So it's not really is it a failure, or is it just another step? Is it, again, it's the old adage, Thomas Edison found 1,000 ways to not invent a light bulb. But but again, failure is an option, and that's all part of the process.
Well, I think you're right, and I think, she made a really good point. Failure isn't just an option, but it's a good thing. I think attitudes shift over time, and I think especially since we tragically lost two of our space shuttles, people like to avoid failure. It's extremely unpleasant. But if you think about failure as a learning experience, if you don't call it failure but you call it a testing something to its limits, then it becomes a little bit more palatable. Just to give you an example, when Boeing, for example, designs a new airframe, one of the tests that the FAA requires is to take an airframe, doesn't have to have the engines on it or whatever, but you put it in a hangar and you start putting sandbags on the wings, and you keep loading up the wings to measure how much they spring down under the weight of the sandbags, and see if it tracks with your predictive models, so that when the airplane's flying, you know how strong the airframe is. The last test they do with every new airframe is they keep adding sandbags until it actually breaks. And when it breaks, you ask yourself, did my models predict the breakage load? And where did it break? What part of the wing cracked? And is that where we would expect it to crack? Because that's the weakest link. And that's a way to check your models. Of course, it destroys your first airplane that you built, but it's a valuable learning lesson. And things that are related to human safety, we still do that kind of testing, but we don't see that kind of testing too often. So when I'm working on space missions, or even aircraft missions, but space missions especially, because we send things out in space and we can't go out and fix them usually, I always encourage the project managers to budget a little extra money to make two of the item. You make the one you're going to fly, but make an extra one and put it in the lab and break it. Push it after you've gotten all the data out of it, push it hard enough to break it so that you really know what the failure mode is. And we've learned the hard way that when you don't do that, it can be pretty challenging and expensive to come up with a fix for something that's out in space.
Well, as you mentioned, just with the gearboxes on Opportunity, I mean, if gearbox worked here, it would have failed immediately, right?
And every cloud has a silver lining. We built a space station over the last couple decades, and it's been a phenomenal research tool, and it is to this day. A lot of great work going on up there. When they were designing and building a space station, they had to come up with some really interesting bearings that help the space station generate electrical power. So the space station is circling the globe every hour and a half or so, and in order to generate lots of electricity, the solar panels have to be kept pointed towards the sun. And for for the most part. And the way we do that is we've got a kind of like a clockwork mechanism built into the space station, and big bearings that are about 10 feet in diameter that hold the solar panels, and the drive motors rotate those bearings very slowly, one rotation every 90 minutes or so. And we launched the space station, and it's got 2 solar wings, and one of the sides, the bearing was turning just fine for 3 years or so, and we put the other side into action, and it failed after 3 months. It started to get hard to turn and started to kind of shake the space station when it was turning, and we sent the astronauts out there to figure out what was wrong, and they found a damaged bearing with lots of wear debris, and I was on the team of specialists to try to figure out what went wrong and how to fix it. And after about 6 months of very, very difficult research and development and testing, we figured out that the bearing that failed because it destroyed itself because it wasn't lubricated well enough. And what was interesting is that it was a brand new design. No one had ever done anything like that before, and this particular bearing had a failure mode where it could eat itself up if the friction rose a little bit higher than normal levels. But since it was the first time anybody had built one, we didn't know it. But when we went back into the lab records, when we were looking at testing, we tested these joints before we launched them, we could detect the onset of failure. It's just that we had run the required number of test cycles prior to launch. We got to that point, and the project manager said, okay, we've done enough, it works well enough, let's launch it. And I look back and think to myself, if we had just built an extra one of those bearings
and broke it
and kept running it beyond that minimum requirement, we probably would have seen that failure on the ground, and we could have done something about it before launch. Mm-hmm. The upside is that a lot of good people did a lot of good work, and the astronauts went out on the outside of the space station and replaced the broken parts. We added a little bit better lubrication, and the thing's been running fine since then. So we fine-tuned our skills in terms of how to fix things in space, and it turned out to be a story with definitely a silver lining.
Yeah. Last question I have, Chris. Is there a PSPM 500 somewhere down the road?
Everybody keeps asking me that.
It probably isn't, next year, but I mean, can you see something?
Well, I definitely can. I talked about the need to recognize long-standing problems, and one thing I can say is I do feel a lot of phone calls and emails from people that say, hey, I want to take your NASA award-winning technology and put it in my car engine, and I won't have to change the oil. And I tell people the same thing. I say, look, if the temperatures are low, like a couple hundred degrees Fahrenheit or less, use conventional materials because they're going to give you lower friction, longer life, and a lot lower cost than these exotic materials that have that unique capability of operating at higher temperature. And one of our holy grails in tribology, or friction and wear, is to come up with a high temperature material that has friction as low as Teflon. So the NASA PSPM 400 materials, they work pretty well, but the friction is about 2 or 3 times higher than you get with Teflon and graphite and grease. So what I do is constantly I'm reading the literature. I read the physics journals. I read the chemistry journals. I read popular science and whatnot. And if somebody pops up on the horizon with a new material, whether it's graphene or something like that, I want to know its properties. Does it have high temperature capability? Is it soft enough such that it might give us lower friction? Maybe that's the magic ingredient that'll go into PSPM 500. And if something like that comes along, sure, we'll do the next generation. And until then, we'll just keep working on everything else and all of the above.
All right. Well, Chris, again, congratulations on your award, and we appreciate you coming in this morning. And of course, we'd sit here and talk all day. Yeah. So again, and again, Debbie's over there in the corner. Thanks again for everything that you did to get Chris in here this morning. We really appreciate it. So
and to answer that question that's on everybody's mind, change the oil in your car according to what the manual says.
There you go. Right from NASA Glenn. There you go. All right, Chris, again, thanks again for coming in this morning.
My pleasure.
Appreciate it. It's 51 minutes after 7 o'clock here on 97.1 Wadsworth Community Radio.